In this video, we are going to discuss about the real gases. At the end of this lesson, students should be able to explain the ideal and non-ideal behaviors of gases in terms of intermolecular forces and molecular volume. Students also need to explain the condition at which real gases approach the ideal behaviors. What is exactly the real gases? Real gases are non-ideal gases whose molecule occupy space and have interactions. They do not behave according to the assumptions of the kinetic molecular theory. The real gases are the gases that deviate from the ideal gas law, which is also known as non-ideal gas. Real gases has the following features. First, the gas particles have a certain volume. There are force of attraction between the gas particles even though they are usually very weak. The gas is also obeys the van der Waals equations. The deviation of real gas from ideal gas behavior can be shown by plotting PV over RT against pressure at a constant temperature. Observe how the curves of the gases deviate from the horizontal line that representing the ideal gas. The causes of deviation from ideal behavior may be due to the following two assumptions of kinetic theory of the gases. First, the volume occupied by gas particles is very small as compared to the volume of the container. Second, there are no intermolecular forces between the gas particles. Real gases deviate from ideal gas behavior when we apply a high pressure and low temperature. When a gas is compressed, the volume of container is decreased. Thus, the distance between gas particles are getting closer. When the gas particles are closer, the intermolecular force becomes significant. Therefore, the gas is deviate from ideal gas behavior. They are known as real gas. At lower temperature, the average kinetic energy of the gas decreases. This is due to the gas particles that move slower and getting closer to each other. When the gas particles get closer, the intermolecular forces become significant. Therefore, the gas deviates from ideal gas behavior, which is known as real gas. But gases will behave ideally when we apply a lower pressure and higher temperature. When the pressure decreases, the volume increases. This will cause the distance between gas particles become far apart and exhibit less interaction between the particles. Therefore, the intermolecular forces can be neglected. Thus, the gas behave ideally. At higher temperature, the average kinetic energy of the gas particles increases. This is due to the gas particles that move faster and far apart from each other. When the gas particles are far apart, it exhibits less interaction between the gas particles. Thus, the intermolecular forces can be neglected. Therefore, the gas behave ideally. The deviation of real gas from ideal gas behavior can be shown by plotting PV over RT against pressure at different temperature. Remember, there are two conditions of gases to behave ideally. A gas can behave as a real gas when we apply a higher pressure and low temperature. But when we apply a lower pressure and higher temperature, the gas will behave ideally. The real gases obeys van der Waals equation. But do you know what is exactly the van der Waals equation? Van der Waals equation is an equation that can be derived by considering a real gas and converting it to an ideal gas. Since a real gas does not exhibit ideal gas behavior at high pressure and low temperature, the ideal gas equation, which is PV equals to nRT, needs to be adjusted. Two parameters need to be reconsidered. First, the volume of the gas particles, and second, the intermolecular forces between the gas particles. In the ideal gas equation, which is PV equals to nRT, the value of V represents the volume of the container. The volume available for the gas particles to move about in a container is always less than the observed volume because the gas particles occupy a sizable portion of the container. The space occupied by gas particles causes the value of PV over RT to deviate from the predicted value. Therefore, the volume occupied by gas particles must be subtracted from the total volume. Thus, the effective volume can be determined, which is equals to the volume of the container minus the volume occupied by the gas particles. If the volume occupied by the gas particles is equals to Nb, whereas N represents the number of mole of the gas particles and B is a constant representing the volume occupied by the gas particles, therefore, the effective volume is equals to volume of the container minus Nb. The pressure of gas is caused by the bombardment of the gas particles on the wall of the container. But the existence of the attractive forces which act between the gas particles will make the gas particles move slower and give less impact to the wall. Therefore, the pressure exerted by the real gas is reduced, causing the PV over RT to deviate from the predicted value. Since the pressure exerted by a real gas is less than its predicted value, thus it can be expressed as pressure of a real gas less than the pressure of an ideal gas. The term pressure need to be adjusted by adding coefficient n square A over V square, whereas n represents the number of moles of gas particles and A is a constant related to the strength of intermolecular forces between gas particles. Therefore, the adjusted pressure can be expressed as P of ideal gas equals to P of a real gas plus n square A over V square. By substituting the effective volume and the pressure into the ideal gas equation, PV equals to nRT, thus the Van der Waals equation can be written as this, whereas N represents the number of moles of the gas particles, A is a constant related to the intermolecular force between gas particles, and B is a constant representing the volume occupied by gas particles.